In 1903, a group of workers digging a drainage ditch in Somerset, England, pulled a human skeleton out of the ground. It was 10,000 years old, nearly complete. And when scientists finally sequenced its DNA in 2018, they found something that stopped the entire field of anthropology in its tracks. This man, Britain's oldest known resident, now called Cheddar Man, had dark brown to black skin and blue eyes. The combination looked so strange to modern scientists that they checked the results twice. But the DNA was unambiguous. The first people of Britain didn't look anything like the British people of today. And that raises a question that turns out to have a surprisingly complicated answer. How did human skin go from universally dark to the spectrum of colors we see today? And why did it happen at all? The answer doesn't start with race or geography or even sunlight. It starts with a molecule. Melanin is a pigment produced by specialized cells called melanocytes in the deepest layer of your skin. Think of it as billions of microscopic shields, absorbing ultraviolet radiation before it can penetrate deeper and damage your DNA. The more melanin you have, the darker your skin, and the more protected you are. In most mammals, fur does this job. It acts as a physical barrier against UV radiation. And because of that, the skin underneath most mammals' fur is actually quite pale. It doesn't need to produce much melanin because the fur is already blocking the sun. But humans lost their fur, and the reason is directly connected to how we hunted. Around 2 million years ago, Homo erectus developed a hunting strategy called persistence hunting, chasing prey not through speed, but through endurance, running for hours under the direct African sun. But thick fur, excellent at keeping heat in, becomes a death trap when you need to lose it fast. Hominins with thinner fur could sweat more efficiently, hunt longer, and bring back more food. The ones with thick fur overheated and lost. How exactly fur disappeared over hundreds of thousands of generations is a fascinating story in itself. But that's a separate video. What matters here is what happened the moment it was gone. Over hundreds of thousands of generations, fur disappeared. Skin was now directly exposed to the African sun for the first time. Without fur as a barrier, melanin became the only protection available. So natural selection pushed hard in one direction. Melanocytes became more active, more melanin was produced, and became darker. By the time modern Homo sapiens emerged in Africa around 300,000 years ago, every single one of them had dark, melanin-rich skin. Not some of them, all of them. Dark skin wasn't a variation. It was the only option that kept you alive under the brutal equatorial sun. This was the baseline, the default, the starting point for everything that came next. But melanin does something else too, something that would become critically important the moment humans started moving. UV radiation doesn't just damage DNA, it also triggers a chemical reaction in the skin that produces vitamin D, a hormone actually that regulates calcium absorption, bone development, immune function, and reproductive health. And it is this one hormone that would silently rewrite the color of human skin forever. In equatorial Africa, this was never a problem. The sun was so intense that even heavily pigmented skin produced enough vitamin D. Then, around 60,000 years ago, some of those dark-skinned Africans began moving north. The climate was shifting. Wet periods turned the Sahara into grasslands, opening natural corridors northward. Populations followed the herds. And as human numbers grew, competition for resources pushed young groups into unexplored territory. And this is where the physics became a problem. At high latitudes, the sun sits low on the horizon. Its rays travel through far more atmosphere before reaching the ground, filtering out most of the UVB radiation needed for vitamin D synthesis. In winter, which can last 6 months or more, meaningful vitamin D production stops almost entirely, regardless of skin color. Dark skin evolved to block around 90% of UV radiation. In Africa, where UV levels are extremely high, the remaining 10% was more than enough for vitamin D production. But move to Northern Europe, where UV levels might be only 10% of what they are in Africa, and now dark skin is letting through maybe 1% of the original level. That's not enough. Not even close. And the body notices immediately. Without adequate UV penetration, vitamin D production slows to almost nothing. Calcium stops absorbing properly. Bones that should be hardening stay soft. A child growing up in these conditions doesn't look sick at first. They eat. They play. They seem fine. But inside silently, their skeleton is developing wrong. This is where vitamin D stopped being a health issue and became an evolutionary filter. Women with insufficient vitamin D had deformed pelvises and died in childbirth. Their darker skin genes died with them. Women with slightly lighter skin, even just slightly, produced just enough vitamin D to develop normally, deliver safely, and raise children who inherited their genes. Generation after generation, the same brutal filter applied. Lighter skins survived, darker skins struggled, and yet the math never added up. If this filter was running every single generation, dark skin should have disappeared from Northern Europe within a few hundred generations. But the genetic evidence shows that as recently as 10,000 years ago, that's Cheddar Man's time, most Europeans still had dark skin. For 35,000 years, the selection pressure existed, but the skin barely changed. Why? The answer came from an unexpected direction: diet. Hunter-gatherers weren't relying solely on sunlight for vitamin D. Fatty fish, animal liver, eggs, and marine mammals are all naturally rich in vitamin D. A hunter-gatherer eating a varied diet of meat and fish could maintain adequate vitamin D levels even with dark skin, even through a northern winter, even without significant sun exposure. The melanin production didn't need to change because the diet was compensating. Then agriculture arrived, and it changed everything. Around 10,000 years ago, farming began spreading out of the Near East into Europe, and the dietary safety net vanished almost overnight. Early European farmers weren't eating fish and game anymore. They were eating wheat, barley, and grain-based porridge. But why the sudden shift? Agriculture didn't just change what people ate, it changed how they lived. Farming populations were sedentary, tied to fields that required constant labor. Hunting and fishing take time, mobility, and skill. Early farming communities were locked into grueling seasonal cycles of planting, tending, and harvesting. They couldn't afford to send people away for days-long hunting trips. Fish were a luxury for those near rivers or coasts. For inland farming communities, the diet became overwhelmingly grain-based by necessity, not choice. And grain, no matter how much of it you eat, contains virtually no vitamin D. The one backup system that had allowed dark-skinned humans to survive in low-light environments for tens of thousands of years was gone. Now the selection pressure that had always existed became acute. With no dietary backup left, vitamin D could only come from one place: the sun. And the sun was weak. The only women who could get enough UV were the ones with slightly less melanin production. Less melanin meant more UV entering the skin. More UV meant more vitamin D. More vitamin D meant bones and pelvises developing correctly. These women lived. Their darker-skinned counterparts didn't, and every surviving daughter inherited the same reduced melanin production from her mother. Generation after generation, the population's melanin levels were quietly dropping. The skin was getting lighter, not by choice, not by chance, by survival. But this process needed a catalyst. Gradual pressure alone wasn't enough to transform an entire continent. What it needed was a single mutation powerful enough to accelerate everything. And then it appeared. A copying error deep inside one cell, in a gene called SLC24A5. One letter changed out of 3 billion in the human genome. This mutation reduced melanin production by 30 to 40%. One person, somewhere in the Middle East or Southern Europe, was born noticeably lighter than everyone around them, and they were healthier for it. Within roughly 150 to 250 generations, somewhere between 3,000 and 5,000 years, that single mutation had swept through European farming populations entirely. Not because of culture or preference or any conscious choice, simply because the people who carried it survived, and the people who didn't increasingly didn't. But here is what makes this story genuinely surprising. That same mutation, SLC24A5, is almost completely absent in East Asian populations. And yet East Asians also developed lighter skin at northern latitudes. They just did it differently. East Asian populations developed lighter skin through entirely separate mutations in different genes. Different molecular pathways, same biological result. Biologists call this convergent evolution. It's the same process that gave dolphins and fish similar body shapes despite being completely unrelated animals. The environment poses a problem. Evolution finds a solution. Sometimes it finds the same solution twice, which means pale skin isn't one thing that happened once. It's a solution the human body independently invented at least twice, driven by the same equation: low UV, grain diet, vitamin D crisis, selection pressure, mutation, survival.